Dual buck structured high reliability and high efficiency buck boost inverter. Abstract in this paper, dual buck structured single stage, single phase buck boost inverters that use power MOSFETs are presented. The proposed inverters require fewer number of switches, and achieve inverting action through single stage operation. They have no shoot-through problem, therefore, high system reliability can be obtained. The dead time in PWM signals can be minimized or eliminated, which improving the quality of the output AC voltages and increasing the efficiency. In the proposed inverters, MOSFETs can be used without reverse recovery issues of their body diodes to boost the efficiency and increase the switching frequency. The simulation results of this system indicates small distortion in AC voltage form due to no or small dead time requirements in the switching signals. To regulate the AC voltage waveform, a Cook converter topology along with a controller section is introduced. The constant output voltage is obtained for a wide variation of inputs, which is essential for renewable farm-based AC microgrids. Index terms: buck boost inverter, dual buck, high efficiency, high reliability, single stage. Introduction. The full bridge inverter is a popular topology used for power inversion applications. However, its output peak AC voltage does not exceed the input DC voltage. Therefore, for applications in which the output peak AC voltage needs to be greater than the input DC voltage, an additional boost or buck boost DC-DC converter is needed at the front end for voltage boosting. This forms a two-stage inverter system, which makes the system bulky. Two-stage inverters are time-tested and work well. However, they have certain disadvantages such as a large number of power processing stages, complex control, high cost, low reliability, and low efficiency. In a single stage, an output peak AC voltage greater than the input DC voltage can be obtained by using a full bridge inverter followed by a low-frequency step-up transformer. However, the bulky transformer increases the volume, loss, and system cost. To overcome some of the mentioned drawbacks, single-stage buck-boost inverters were introduced. The dual buck-based topology guarantees increased robustness since the DC link cannot be short-circuited by a shoot-through event. The dual buck structure is given below. The basic concept of a dual buck inverter is introduced in this paper. Its basic switching cell is a unidirectional buck circuit, which consists of one switch and an external diode connected in series to it. Therefore, no short circuit is possible, and high reliability can be achieved. The inductor current does not flow through the body diodes of the switches, but freewheels through the external diodes, D1 and D2. Therefore, the reverse recovery issues and related losses can be reduced by choosing external freewheeling diodes with good reverse recovery features, and a MOSFET can be used to boost the efficiency and increase the switching frequency without reliability issues. In this circuit, the body diodes of switches are not shown because they do not conduct current. Dual buck structured converters use the structures shown in Fig 2 as the basic switching cells. In recent years, dual buck structured DC-AC inverters and multilevel converters have been proposed through significant efforts in research and development. In this paper, novel dual buck structured buck boost inverters are proposed to realize high efficiency and reliability. They are symmetrical single-stage inverters. Phase inverter can be further expanded into a three-phase inverter in future. It consists 6 inductors, L1, L6, 2 leg capacitors, C1, C2, 4 switches, S1, S4, MOSFETs, 4 diodes, D1, D4, and 1 output capacitor, CO. C1 and C2 serve both as filter and snubber capacitors, and CO filters the voltage ripples of output voltage. L1, L6 are filter inductors. In addition to filtering, L1, L4 also protect against shoot-through problem, therefore, the dead time between the switches can be minimized or eliminated. In addition, L1, L4 prevent inductor currents from flowing through the body diodes of S1, S4. The inductor current freewheels through D1, D4, which are chosen externally. 2. Proposed system. In the proposed system, the series inductors are removed and an additional Cook converter is introduced. The DC source is given to the input of Cook converter. The wide variation of input DC is controlled by Cook converter controlling section. The controlled output is provided for the single-stage buck boost operation. Filter capacitor is used to reduce ripples. An equational controller is additionally used to control the varying input of Cook topology in order to obtain the constant output, VIN2. The figure below shows the circuit diagram of the proposed system. At any given time, 2 switches operate complementarily at high frequency and with a finite dead time for the buck boost section. The dead time is needed to decrease the circulating currents. For the positive half cycle of the output voltage, VO0, S1, and S2 operate at high frequency, whereas S3 is kept on, and S4 is kept off. For VO0, S3, and S4 operate at high frequency, whereas S1 is kept on, and S2 is kept off. Within a switching cycle, the inverter has 3 switching modes, as discussed below. 1. Mode 1, S2 is on, and L2 stores energy from the input source. 2. Mode 2, this is the dead time mode, S1 and S2 are both off. 3. Mode 3, S1 is on, and L2 delivers the stored energy to the load and C1. During the positive half cycle of the AC output voltage. Similarly, for V00 we obtain, where VC1 and VC2 are the voltages of C1 and C2, respectively, VIN is the input DC voltage, VO is the peak of VO, and D1, T, D2, T, are the duty ratios of S2 and S4, respectively. The output voltage is the difference between 2 capacitor. 3 simulation results of the system. The existing dual buck standalone single-stage single-phase inverter is simulated in MATLAB/Simulink. The switches are triggered by means of PWM switching strategy having no dead time. The output AC waveform is distorted in buck and boost action. The simulation model of existing system is shown in Fig. 5. The modified dual buck standalone single-stage single-phase inverter is also simulated in MATLAB/Simulink. Here an additional Cook converter and a controller section is introduced. The switches are triggered by means of PWM switching strategy having no dead time. The output AC waveform is not distorted in both buck and boost action. For comparing buck operation is explained here. The simulation model is shown in Fig. 7. Here series inductors are removed from main circuit as modification which have less effect in the overall buck boost action. The input used is 200 VDC and output is of 100 VAC. The input and output waveforms are follows. The varying input is provided to the Cook converter with VIN reference is chosen as 200V and VO reference as 100V. The output of Cook converter is provided as the input to buck boost section. VIN reference value is 200 VDC. Duty ratio is less than 0.5 for buck action and greater than 0.5 for boost action. From the figure the capacitor voltage is initially charged to 200V, input voltage. During the positive half cycle of AC output voltage VC1 goes positive, charges, and during the negative half cycle of output AC voltage capacitor VC2 goes positive. The operation of Cook topology is based on capacitive energy transfer which is more energy efficient. By THD improvement the power quality of the system is made higher. The THD analysis of the existing and proposed single-stage inverter is given below. For conclusion. In this paper, a single-stage single-phase dual-buck structured buck-boost inverter is presented. The single-phase inverter is studied and analyzed various features like high reliability, low output AC voltage distortion and high efficiency. The converter can be designed to work at higher switching frequencies to decrease the volume of passive components and a small high-frequency common mode voltage, which makes the proposed topology suitable for PV inverter applications. The existing system shows little distortions in its output voltage waveform, THD 10.11. To reduce these distortions, a controller section is introduced. In addition to this, a coupe converter is provided to the input section of buck-boost inverter to get constant output with a wide variations in input. This is applicable to photovoltaic standalone power systems which require stable output.